In this section, we are starting with the third module, operational amplifiers. Actually, operational amplifiers is an extension of our differential amplifiers. In this module, we need to discuss different type of, what are the basic parameters, performance parameters of OPAMP, and different type of operational amplifiers, that is one stage OPAMP and two-stage OPAMP. Okay. In this one-stage OPAMP, the working of one-stage OPAMP is nothing but it's exactly similar to our differential amplifier, or a single differential amplifier. We can call it as a one-stage OPAMP. The circuits that we discussed in differential amplifier is equally applicable in one-stage OPAMP also. Okay, and two-stage OPAMP, it used to improve the gain as well as the output swing of the one-stage OPAMP compared to one-stage OPAMP. So in this section, we will discuss basic block diagram of operational amplifier, what are the different parameters of operational amplifiers, and different type of one-stage OPAMPs. One-stage OPAMP. In one-stage OPAMP, similar to our differential amplifier, it can use resistive load, or diode connected load, or it can use current source load, or it can use cascaded configuration, or it can use current mirror also, that we didn't discuss in differential amplifier. Current mirror load. In a differential amplifier also, there is a current mirror load configuration, which actually basic advantage of this current mirror load is, from this current mirror load we can take single ended output with the gain is exactly equal to the gain of two-sided output. For an op-amp, we have, in earlier case we found that two inputs are there, or we will give some V in between two terminals, and output was also taken between the amplifiers from V out 1 and V out 2 plus minus. Here we will take V out, okay, in normal differential amplifier. And if we take only output from one of the amplifier stage, if it is from V out 1, we will get gain only minus Gm into Rd by 2. Here also it is Gm into Rd by 2. Okay, only half of the total gain we will get if we consider output in a single-ended manner. But if we use current mirror load, it can give single-ended output whose gain is exactly same as that of normal amplifier, that is Gm into Rd, where Rd indicating the resistance seen at the drain. That resistance may vary with respect to diode connected load, current source load, or cascaded load, etc. that we derived in our differential amplifier, different type of differential amplifiers. Okay, so now we'll go to the first we will start with the basic features of operational amplifier. As we know, it must have very high differential gain and very low common mode gain required. The operational amplifier's features are also the same. It must have very high voltage gain, differential voltage gain, and it must have high input impedance and low output impedance. And the performance parameters of OPAMP, the OPAMP as well as the differential amplifier will be the same: high differential gain, and in terms of IC or the operational amplifier, some other parameter is also there. We know CMRR, common mode rejection ratio, power supply rejection ratio. CMRR is nothing but that AD by AC, differential gain by common mode gain. And another thing is there, the offset present in the output, or offset present in the input, offset required at the input side. And output swing is one of the parameter, what range output we can produce, and the noise performance, and input impedance and output impedance, And next, the power dissipation for any unlock circuits. One of the parameters is power dissipation, and the most important parameter is slew rate. It indicates the speed of operation, as well as how fast it can vary the how fast it can respond to the input signal. And all these parameters are we learned in our linear integrated circuits. So please go through that one and please study the definition of each parameter, because we have some 4 mark questions in our university exam. Actually 3 marks, right? That question is there, so you need to answer that one. So for that you need to go through the definition of parameters, and this is a simple, very basic block diagram of a general OPAMP. OPAMP consists of, we said OPAMP consists of differential amplifiers. So here it have 4 stages: 1, 2, 3 and 4. All stages are simply amplifiers. In that, first 2 stages are differential amplifier. The first stage is a the differential amplifier with the 2-stage output or two-ended output. Okay. And the second differential amplifier is nothing but a normal amplifier, normal differential amplifier, but it has a single-ended output. That output is used to drive the remaining high gain amplifiers to boost the gain. The first differential amplifier, this one, is used to improve the differential gain, reduce the common mode signal effect, noise effect, etc. And this differential stage must provide the high input impedance of the entire differential amplifier. Okay, so these must provide high input impedance, high CMRR, actually high slew rate also from this differential pair. So this is very crucial, and this will design based on low noise amplification, and we will consider so many design criteria for designing this one. From this one we will take two-sided output that will reduce the effect of accumulation of DC in the propagation. And second stage also a differential amplifier, because from here we are taking two-stage output, here also we are using a differential amplifier, and the output of this differential amplifier is single-ended output. Here we will use the current mirror load circuits. Okay, current mirror load circuit, which will convert the differential input into a single stage output, and then we will use a high gain amplifiers, the single-ended input high gain amplifiers, and the final stage is a buffer which is used for impedance matching. Okay, and this is a basic block diagram, and the buffer will provide low output impedance for that operational amplifier. Then next we will discuss, I will share the material for this definition of offset and CMR, etc. Just go through that. So next we will start with a different type of single stage OPAMP. As I said, that single stage OPAMP, the circuits are same as that of our normal differential amplifier. So we are not going to discuss in detail, because we already discussed the differential amplifiers, differential amplifier with a resistive load, diode connected load, etc. The same derivation you can apply in this OPAMP also. Okay, the circuit is same as that of the normal differential amplifier, and here some capacitor is used to take output load. Okay, and gain of this one we can analyze using in operational amplifiers. You can directly use half circuit symmetry to analyze that circuit. Half circuit symmetry, so it is easy to analyze all operational amplifier circuits. Okay, and you will get the gain is AV equal to minus GM. GM is the transconductance of M1 and M2 into RD parallel R0, where R0 is the output resistance of this M1 and M2, assuming two identical transistors. And the capacitor CL will limit the bandwidth of the operational amplifier. And if we replace that resistor RD with the current source load, the RD value of the current source load will changes to R0 of the connected device. So for current source load, here we are using PMOS. Okay, PMOS, and in the lower end we are using NMOS. So here the load resistance is RO PMOS. Here it is RO NMOS. So we will get the gain is nothing but GM of the NMOS. So GM of N minus GM of N RO N parallel to RO P will be the gain of this circuit. Here also we will use half circuit symmetry to derive the gain of the amplifier, and the bandwidth is limited by the capacitor CL. For deriving that, we need to assume the MOSFETs are symmetric, like that M1 and M2 are symmetric or identical, and M3 and M4 are identical. The parameters are same. Then only we can apply a half circuit symmetry. And this is the analysis of uh, differential amplifier or OPAMP with the current source load. Similarly, you can do operational amplifier for diode connected load also. You can apply the same concept, or you can just copy that from the differential amplifier stage. And one important thing that we missed in differential amplifier analysis is single-ended output or using current mirror load. Okay, the same question they can ask in differential amplifier or in case of module 2 as well as in module 3. A single-ended op-amp with, sorry, not single-ended, single stage op-amp with a single-ended output, or single stage op-amp with the current mirror load, or how the current mirror load improve the gain of a single-ended differential amplifier. In general, if we take single-ended output, we are expecting gain of minus GM RD by 2, or in case of this one, we are expecting an output minus GM R OP parallel to RON divided by 2, because if you are considering only single-ended output. But due to the current mirror action or due to the current mirror load, here we will get an output. The output value is equal to our normal differential amplifier stage, like GM into ROP parallel to RON. So we need to prove that. To prove that on, we will apply our basic idea itself. Okay. So to prove the gain of this differential amplifier stage is this one, we will evaluate the transconductance as well as output resistance of this one. First we will discuss the basic structure of CMOS differential amplifier or op-amp with the current mirror load. So if we consider the lower half, if we consider this lower half, this is identical to a normal differential amplifier, and if we consider the upper half, this portion is equivalent to a current mirror. Okay, because in M3 there is a diode connected configuration, and that same gate is connected to M4. So using M3 and M4, here a diode connected configuration, or sorry, current mirror circuit is formed. Due to that, this value of ID3 or ID1 or ID1 is same as that of this ID4, not ID2. It must be ID1 and ID3 must be equal to this ID4, because there is no current flowing through this direction. ID1 and ID3 are same, and which must be equal to ID4. So that is the concept of current mirror idea. From the current mirror, we will use that idea to derive the gain of this configuration. So gain of this configuration is derived by, we need to evaluate the effective transconductance of this on GM and the output impedance R out. Then we can write the gain is equal to minus GM R out. Okay. To evaluate in the transconductance, what we will do, we will short our output, and we will short our output, so output becomes 0, output voltage becomes 0, and we will find the short circuit current Ix, and we will find the GM value as or Ix or I out you can use I out by the total V in. From that we can find the value of transconductance. Next, to finding the output impedance, what we will do, erase all, we will give a test voltage here. We will give a test voltage here Vx, and we will find the current Ix. Then the R out is Vx by Ix. So calculation of GM somewhat easy, but calculation of R out is require some steps or some small signal modeling to evaluate R out. Okay. So for the analysis, we are assuming all the so here I missed this one. Arrow is here. Okay, the transistor M1 and M2 are identical in MOS, and M3 and M4 are identical PMOS. Its transconductance and output resistance or channel length parameters are identical. Okay, and to find the output impedance, not output impedance, effective transconductance, we will model the circuit like the output is shorter to ground. We need to find the current I out, and we are given the voltage V in 1 by 2 and V minus V in 1 by 2 in M1 and M2. M1 and M2. Okay, so we know here these currents ID1 equal to ID3 and which is equal to ID4. All these are same. Okay, and ID1 is nothing but we know it is GM into erase. Here ID1 is nothing but ID1 equal to GM into GM1 into V in 1 by 2 V in by 2 V in by 2, and ID2 is V in 2 is here GM into V into. So ID1 is nothing but GMN into V in by 2, and ID2 we can write it as GMN into minus GMN into V in by 2. These two we can write directly from this one, and also we know ID1 equal to ID3 which is equal to ID4, and from this one I'm erasing all. From these split up we can simply write I out equal to ID2 plus ID4 or ID2 minus ID4. Okay, its ID4 direction is opposite, so minus ID4, and it's become ID2 is minus GMN into V in by 2. ID4 is nothing but ID1 itself, so it is again minus GMN into V in by 2. So we will get it is minus GMN into V in. Or we will get I out by V in, the effective transconductance GM equal to minus GM of N. Okay, then we will proceed to the next step to find the R out of this circuit. To finding the R out, we will apply a test voltage at the output side, and we need to find the current Ix. And in this analysis, we will short all the inputs, shorted to ground. Inputs are grounded and VDD is grounded. All the supplies are grounded. And current source, we are assuming it is open circuited. That current source at here, we are assumed it is open circuited, or this point is AC ground. We have a basic idea in differential amplifier. This point, the common terminal, is AC grounded. So by analyzing this one, we can prove that the R out value is nothing but RO on or RON parallel to ROP. We need to prove that this R out is RON parallel to ROP. We will keep this in mind because we need to conclude that this R out is equal to this one, RON parallel to ROP. So for that, first here we will evaluate M1 and M2. In M1 and M2, the gate is grounded. So, and this have same potentials. So this will be, we can replace this gate is grounded we can replace it with VGS equal to 0 or the input voltage is 0, it will replaced with its equivalent resistance R0N. So here this R0N is parallel to this R0N. This circuit we can simply, this entire circuit we can replace with a single resistor whose value is R0N. Okay, first replacement, these M1 and M2 are replaced with its equivalent resistance, that is R0N. So due to the series connection of this one, here it's become 2 R0N. And again, next we will replace this M3. M3 is a diode connected configuration. So that diode connected configuration, it is connected from here to this one. So if we replace this diode connected configuration, it will be replaced with a resistor whose value is 1 by GM3 we know. Then the modified circuit diagram looks like this one. The lower part is replaced with the 2 RON and the upper part is with the diode connector configuration with the 1 by GMP because it is a PMOS. And M4 will be there, and to evaluate the actual resistance we need to use small signal modeling for M4. Small signal modeling. Small signal modeling for M4. In the small signal analysis, that replaced with a gate source voltage. Here it is GMP, VGS4, R0P. We need to consider this R0P because we need to get the output resistance in terms of RON parallel to ROP. So when we come to this figure, sorry, maximum zooming, okay, I can't zoom more. So here I need to express Ix in terms of Vx. Okay, here Ix is split into Ia and the current in this direction, and VGS4 is across this one. We can define Ia in terms of this voltage is Vx, so we can define Ia as that Vx divided by these resistance, like 1 by GMP plus 2R on. Okay, so Ia is expressed in terms of Vx, and we need to express these two currents. These two currents are also in terms of Vx. As this is Vx, current through R04 is Vx divided by R04, and this one is GMP VGS4. So VGS4 we need to express in terms of Vx. Here we can express VGS4 in terms of Ia, that value is Ia into 1 by GMP, and Ia is expressed in terms of Vx. So we can convert all the currents in terms of Vx, and then we can find the output impedance. So here we got all the things. The total current Ia, not Ia, Ix is consist of Ia plus this GM VGS and this one Vx by R04, and in that we will rewrite Ia value, and we here also we will rewrite Ia value. Then we can express Ix in terms of Vx alone, and we will get the value of Ix is equal to 2 times Vx by 2 R1 plus 1 by GMB plus Vx by ROP. As 1 by GMB is very small compared to RO, we can neglect that, and it will reduce to Ix equal to Vx by RON plus Vx by ROP, or Vx by Ix is equal to 1 by RON plus 1 by ROP, or it is nothing but a parallel combination. So ROT is nothing but the parallel combination of RON and ROP. So the actual gain of, the overall gain of differential amplifier or the OPAMP with current mirror load become GM into Rout, which is AV equal to minus GMN into R01 parallel to R0P. If we take the output from the to get the non-inverted output, we can use a non-inverting amplifier also. So there is no reduction in gain even if we are taking single-ended output. That's the advantage of using current mirror load. Okay, so we need to continue with the cascaded configuration as well as telescopic and folded cascade that I will take in the next section. Okay.